So in calculus, we have these things called critical points, and they're real straightforward for calculating them. You just take a derivative, you set it equal to 0, and then you solve. And the critical points are whatever your solutions are after that. Or the critical points are also where the derivative fails to exist. So if you have a divide by 0 error in your derivative, that's a critical point. Okay, and so we want these because they identify potential places where we could switch from decreasing to increasing. They're potential places where we have local maxes and local mins. Okay, so it's probably best to just learn by doing. Let's take a derivative, like I said, for finding these critical points. Pretty straightforward there. Set it equal to 0, like I said. Critical points are where the derivative equals 0, where we have those horizontal tangents. And then solve this equation for x. You want to add 2 to both sides, divide both sides by 3. So x is going to be positive or negative square root of 2/3. And I got that because I added 2 to both sides, divide 3 from both sides, and then a square root to cancel out a squared means we need to consider both positive and negative. Okay, so those are the critical points. We need to figure out whether they really are maxes or mins. So square root of 2/3 and negative square root of 2/3, I'll just draw those on a number line real quick. Oops, it's the square root of the whole thing. Okay. We need to test out points to the left of these critical points and to the right of these critical points to see whether they really are maxes or mins. So if we test out f of 0, and actually it's not in function notation, but it is a function. If we plug 0 into this function, we get out y equals 4. Okay? And so what do we get for a y value when we plug in negative square root of 2/3? So 2/3 square root and negative. So I'm plugging this number into the original equation. So if I cube it, and then this is a negative times a negative is going to make a positive. Oh, I forgot what the cubed one was, but this is the middle term. So we got 2/3 square root negative plus that term plus 4. So I just used my calculator. I got 4.81. And now that's my critical point. I also have to test something to the left as well. So let's do something nice and easy. Let's test -1. If I plug in -1 into that equation, -1 cubed is -1. -1 minus 2 times -1, that's positive 2. So 2 plus -1 is 1. 1 plus 4 is 5. So I plugged in -1 and I got out 5. So, man, I wish the book would start with something that lets you have some success. But if you find your derivative, you set it equal to 0, you get these critical points here at x equals negative square root of 2/3 and x equals square root of 2/3. It didn't turn out to be a maximum this time because look, we were bigger to the left and smaller to the right. And here, let's graph this real quick. X to the third minus 2x plus 4. X to the third minus 2x plus 4. Oh, it should be. Should be a local max. What did I do? I plugged something in wrong. Okay, well, hold on. This is 4.81. I got 4.81. They got 5.0. So apparently I did my calculator work wrong here. Let me double check this one. When you plug in x equals negative 2/3, I should say x equals square root of negative 2/3. And it's negative. Okay, if I raise that to the third power, should be still negative. That's fine there. And then it's 2 times that result. So 2, wait, let's do 2/3 square root. Oh, I forgot to multiply that by 2. That's what I did. Okay, so I miscalculated. There's a lot to miscalculate there. That's hard to plug in. So this should be y equals 5.08. Okay, so this x coordinate we found, it's a local maximum, right? Because it's at 5.08 or something like that. 5.09 when we round. And a point to the left was smaller. A point to the right was smaller. So this 5.08 is the local maximum at x equals negative 2/3. So we got to do the same thing for this one to see if it's really a critical point. I think we just spotted on the graph, but what's the y value when we plug in square root of 2/3? 2/3 square root. I'm going to plug that in, so we want to raise that to the third power. So 0.54433. Let's see if I can remember that. 0.543. I got 2.911, if I didn't mess anything up this time. And so, look, this is our critical point. This is our other critical point. We want to test a value to the left and to the right to verify that it really is a critical point. Sorry, it's definitely a critical point. We want to test the value to the left and to the right to verify that it really is a max or a min. So right now it's looking like a min because going from x equals 0 to x equals square root of 2/3, we drop down, right? But we need to test like x equals 1, something to the right, to verify that. If you plug 1 into this function, 1 to the third is 1, 1 minus 2 is negative 1, negative 1 plus 4 is 3. And look, the function's starting to rise to the right of it. So the number to the left is bigger. The number to the right is bigger. Therefore, this is our minimum. Square root of 2/3 is a local minimum. Okay, and then you can verify that graphically. Look, Desmos does it for us, right? But those are our local maxes and local mins. We were able to do it without relying on Desmos, just exclusively through calculus. So that's what critical points help us find. Okay, sorry about that miscalculation halfway in there. Okay, so for this next one, y equals x to the third minus 3x squared. We want to do the same thing, take a derivative, and then set it equal to 0. There's our derivative. We set it equal to 0. I think this one's going to be a lot nicer. It's quadratic, right? So I want to try to solve it by factoring. Let's factor out a 3 from everything. And then you need to finish factoring by finding two numbers that multiply to be 1, but add it to be negative 2. So that's x minus 1 and x minus 1, sorry. Because negative 1 times negative 1 makes positive 1. Negative 1 plus negative 1 makes negative 2. And then when you're solving quadratic, you set each factor piece equal to 0, but in this case they're both going to give us the same 0. The only critical point we found was x equals 1. So that's easier than the last one. That just means we need to test out points to the left and to the right of x equals 1. So here's x equals 1. So let's find out the y value when x equals 0. That's a point to the left. So if I plug in 0 into the original function, 0 minus 0 plus 0, that's going to be negative 2. And then what's the y value when x equals 1? So 1 minus 3 is negative 2. Negative 2 plus 3 is 1. 1 minus 2 is negative 1. And then let's test out something to the right, something slightly larger. So if I plug in 2 in here, 2 to the third is 8. That's 8 minus 12. So that's negative 4. Negative 4 plus 6 is 2. 2 minus 2 makes 0. So let's see. To the left, it's a smaller number. To the right, it's a bigger number. So it looks like x equals 1 is not a max or a min. It's a critical point, but it didn't turn out to be a max or a min, unless I did something wrong mental math again, which is possible. Let me check. 1 minus 3 is negative 2. Negative 2 plus 3 is 1. 1 minus 2. No, that's right. Let's look at it graphically. X to the third. So here's our graph. Remember, x equals negative 1 was our critical point. Oh wait, no, not negative 1. It was x equals positive 1. So it leveled off, but it didn't turn out to be a max or a min, because we test those values to the left and to the right. We found out it wasn't bottoming out, or it wasn't reaching a maximum. So that's the lesson there, is that critical points are potential maxes or mins. You've got to test them out to make sure. Same thing on these next ones. Take a derivative. So the 1/2 power comes down because the square root is a 1/2 power. Then it gets reduced by 1, so 1/2 minus 1 is negative 1/2. But then don't forget the chain rule when you take the derivative. The derivative of the innermost function is negative 2x. So 1/2 times negative 2x makes negative x. And then instead of making that a negative exponent, I'm going to put that in the denominator. So there's our derivative. Okay, because 1/2 power, that's a square root. So when I put that in the denominator, To make it a positive power, I just added in that square root back. Okay, remember derivatives are where, critical points are where the derivatives equals 0 or where the derivative fails to exist. So down here, I can see two places where it fails to exist, at x equals 1 and x equals -1. Because if you plug those into the denominator, you've got divide by 0 problems. Okay, but let's find the ones where the derivative equals 0. To get x by itself, I want to multiply both sides by square root of 1 minus x squared. So it makes these cancel out. So I've got 0 equals -x. In other words, we have a third critical point to test, x equals 0. Okay, rough life. But for this one, we have 3 different critical points to test. You might be thinking, why can't I just do this graphically? Why can't I just pull up a graph? You could, but this, sometimes when we're not allowed to have calculators. Okay, so for the situations where we're not allowed to have calculators, I think you probably get the idea, right? You want to test a point to the left and to the right of these critical points. Like if I plug in -1 into my original function, I get out y equals 0. If I plug in 0, I get y equals 0. Y equals 1. And if I plug in +1, I get y equals 0 again. So actually right there we know that this is going to be a local max. At x equals 0, it's a local max. Because a point to the left and a point to the right between these two critical points is, they're both below it. Right? This is bigger than both of these. And if you're wondering how far to the left and how far to the right can I choose, you just make sure you don't go past the next critical point, because the next critical point is the next potential direction switching. Actually, so this isn't too bad, because now we could just test x equals -2. If you plug -2 into this function, -2 squared is 4. 1 minus 4 doesn't exist, right? So actually anything to the left of x equals -1 isn't going to exist, so this is a local min here. And then if you try to test something bigger here, if you try to test x equals 2, that also is going to give you a square root of a negative. So these are local mins because they're actually the end point of the domain. Those are as low as you can go. Okay, and then this last one, this is a cube root. So another way of writing this to make it more derivative friendly. Just make it a negative exponent, because that's in the denominator. That's a 1/3 power. So I brought it up into the numerator. It's a negative exponent. So when I take a derivative, it's easier in that form, isn't it? So -1/3 minus 1 makes -4/3. And then we need to multiply that by the derivative of the innermost function, so the derivative of -2x. Okay. Because of the chain rule. So negative times a negative makes a positive, so this is 2x over 3 when I multiply these terms. And then you can make that be a positive 4/3. What's an easier way of writing that? I guess that's it. Okay, put it in the denominator. And so remember, critical points are where the derivative equals 0 or where the derivative fails to exist. So here's my derivative. Where does this equal 0? I can multiply both sides by the entire denominator and I just get 0 equals 2x, right? In other words, x equals 0. So that's one critical point. It's one potential max or min. But the places where the derivative fails to exist are at x equals 1 and x equals -1, just like on the last one, because that would cause divide by 0 problems down there, right? My brain's getting foggy, so I'm going to double check to make sure I haven't messed anything up. No, it looks good. Okay, so those are more points that we have to test just like we did in that last one. So here's our number line. X equals 0, x equals -1, and x equals +1. So what are the y values? Are these really maxes or mins, or are they just false maxes or mins like on this one we did up here? So if you plug in 0, that middle critical point, 1 minus 0 is 1, cube root of 1 is 1, so that gives us y equals 1 for a value. And if you plug in 1, that's going to give a divide by 0. So it's the same thing as the last one. These parts are going to be, actually it's not defined at these exact locations. So these aren't local maxes or local mins because it's exactly -1 and +1. The function, the yeah, the function does not exist. You can't plug in 1 because that would cause a divide by 0 error. So y equals 1 is the only place I really want to analyze. So I want to plug in negative 0.5 and positive 0.5 in here. Okay. But you know how to plug and chug in a calculator. Let's just check it out real quick in Desmos, see whether it was indeed a max or a min. Oh, it's cube root 1 over 1 minus x squared 0.33. So there it is. At x equals 0, we had a local min. The critical point did help us find one that time.